Welcome everyone to this week's Western Hemisphere Virtual Symplectic Seminar. We're very happy to have Kai Hugtenburg from Edinburgh speaking on the cyclic open-closed map, U connections, and R matrices.
Thank you very much for inviting me to speak here. Unfortunately, I only have one screen right now, so it means it makes it more difficult to keep track of when people are looking very confused. So if you are confused, just ask, because I won't be able to tell. Oh, this is great. I already start on the wrong page of the slides. How do I get back? There we go. That's where I want to start. Okay, cool. So yes, the whole story will start like with enumerative mirror symmetry, which was people came up with in 1999. So it's Candela, De La Osta, Green, and Parks. And their idea was that there exist these pairs of spaces, X and Y, where X is a symplectic manifold and Y is a complex manifold. And the idea is that the Gromov-Witten invariants of X correspond to some period integrals on the complex space Y. And then in 1993, Morrison formulated this by sort of packaging this data, for example, Gromov-Witten invariants of period integrals, in a variation of Hodge structures. And moreover, he said that if you have a splitting of this variation of Hodge structures, then you can obtain some enumerative invariants. Don't worry if you don't know any of these terms yet. I will explain them in a bit. And this was all in the Calabi-Yau setting. But then in 2001, Baranikov sort of defined the analog of this in the Fano setting. And instead of a VHS, he called this a variation of semi-infinite Hodge structures. And I will call these like formal TP structures, and I will define these in a minute as well. Then the idea is that that Kontsevich came up with is that instead what you should actually look at is a sort of a deeper kind of mirror symmetry, which is a homological mirror symmetry between X and Y, which says that the Fukaya category of X is quasi-equivalent to the derived category of coherent sheaves on Y. And he conjectured that if X and Y are homologically mirror, then actually their enumerative invariants, or the Gromov-Witten invariants, and the period integrals of Y are actually in correspondence. But this is, in most cases, still an open problem. So what is the idea of the proof to show that homological mirror symmetry implies enumerative mirror symmetry? Well, the first step is to associate to the, well, I'll explain it for the A side, so for the symplectic side, is to associate like this VSHS or formal TP structure to the Fukaya category. The next thing that you have to do is to show that this TP structure agrees with the quantum TP structure. I will define these in a minute, so don't worry. And then the last thing that you need to do is that if you have this TP structure, you can equip it with a splitting and obtain enumerative invariants. So on the TP structure associated to the Fukaya category, you need to come up with the correct splitting to obtain the Gromov-Witten invariants. And this allows me to introduce a bit of my talk. What I'm going to do is to tell you first what these formal TP structures are. And these were defined by Getzler, Katsarkov, Kontsevich, Pantev, and Kliarov. Then I will tell you of a theorem that relates the formal TP structure associated to the Fukaya category with the quantum TP structure. This was first done by Ganatra, Perutz, and Sheridan, and I add some things to this. And then finally, I will tell you what the story is with this splitting. And this is not known in general how to obtain the correct splitting, but there have been works that do this in certain cases. So for example, Ganatra, Perutz, Sheridan do this for Calabi-Yaus, and Mormon 2 do this when the quantum cohomology is semi-simple. And in my talk, I will give some interesting applications of the splitting. Okay, so to get started, let me tell you what these TP or TEP structures are. So just the basics, you start with a field of characteristic 0, and we just have some ring R or some algebra R over this field K. And then we just say that like the TEP structure is going to be defined on this E, which is a finitely generated R join U module. And type structures were defined by Hertling, and we're going to consider formal type structures. And the formal is that we were using with power series in U, whereas Hertling actually talks about convergent power series. But for us, just a formal structure is enough. And what is a T structure? A T structure is a connection just sort of on the base. So you take derivations on R, and then that is the input for the connection. And these connections have a pole of order 1 at U is equal to 0. So this is what this map sort of to U inverse of E denotes. Then an E structure is a connection which now goes in the direction of U. So it's like connection d by du. And this one has a pole of order 2 at U is equal to 0. And then finally, we have the P structure, which is a covariantly constant pairing on E. And you require that if you take E tilde, which is E modulo U, that this restriction of the pairing to that is actually a non-degenerate pairing. And just for people who have heard of VSHS before, is that a VSHS is what is a TP structure in here. And a VHS is a Z-graded TP structure. But the main reason why I talk about these step structures is because in what I'm going to talk about, this E structure is going to be the really important one. So this connection in the U direction. And this wasn't really considered before. Okay, let me give you some examples. So associated to quantum cohomology, we're going to construct some type structure. So in this case, let's just work over the complex numbers, and our ring is going to be our C algebra R is going to be Novikov field. Then the quantum type structure is given on the quantum cohomology of X with coefficients in the Novikov ring, Novikov field, and we join the formal parameter U. And like as a lambda adjoint U module, this is just the cohomology of X. And what are the connections? Well, we have a connection in the base direction. So this is the T structure, which is sort of nabla Q by del Q. Well, you just do Q by del Q, and you take the quantum cup product with omega. And similarly, the connection in the U direction is just given by derivation in the U direction. And then you have this grading operator in the U minus 1 term, where this grading operator is just like a shift of the usual degree of cohomology classes. And then you take the quantum cup product by C1 in the U to the minus 2 term. And just, you probably all know how quantum cohomology is defined, but in the setting that I am going to work in, you can actually really nicely express the quantum cup product by some push-pull formula. So how do you do this? You take the moduli space of 3-pointed genus 0 curves. So that's maps from the 2-sphere into X. And this has 3 evaluation maps, sort of evaluation at 3 points, like 0, 1, and infinity, for example. And then what you say is that the quantum cup product between alpha 1 and alpha 2 is the sum over all degrees beta of Novikov parameter to weighted by the area, and then you do your push-pull. So you pull the differential forms back to the moduli space using 2 of the evaluation maps, and then you push them forward using the 3rd evaluation map to obtain a differential form on X. Okay, so that's the quantum type structure. Oh, yeah, I forgot to say the pairing is the Poincare pairing. So now the thing is to associate the type structure to any A infinity category. And for simplicity, I will just be talking about any A infinity algebra, which is unital, instead of a category, just that makes the notation a lot easier. But you can do this definition more generally. So first, we need to talk about the Hochschild chains on this A infinity algebra A. So what are these? These are just like a direct sum over all K of A tensor, A quotiented by sort of A modulo the unit. And on here, you can construct 2 differentials, a small b and big B. And then the Hochschild homology of A is just the homology with respect to this first differential, small b. And the thing that we're going to construct a TEP structure on is the negative cyclic homology. So this is the homology where you're taking sort of the total complex of the differential b plus ub. So here again, you have this formal parameter u that we have adjoined. And what Kontsevich and Solbermann conjecture, which was proved by Kaledin in the Z-graded case in 2005, is that if your A infinity category is smooth and compact, then actually this negative cyclic homology is free and finitely generated. And that is one of the things we need, but for it to be a TEP, for us to be able to define a TEP structure on it. But we're always going to assume this holds. And what is a TEP structure? I won't give you precise formulae, but I'll just tell you who has defined it and where you can find it. So there is the T structure, which was constructed by Getzler. So this is the connection sort of that goes in the R directions. It's called the Getzler-Gauss-Mannen connection. The E structure, so that's the connection in the U direction, that was constructed by Shkliarov and Kontsevich-Pantev. And the P structure is also called the higher residue pairing, which was constructed by Shkliarov. And this is some sort of extension of okay, I've forgotten the word. I'm sorry. So we're going to apply this to the Fukaya category. So we're just going to consider closed symplectic manifolds. And then in general, the Fukaya category has these has as objects the Lagrangians inside X. But for us, what we're going to consider is just a single Lagrangian. So we're just interested in just the Floer cohomology of a single Lagrangian. And we're going to follow the technical setup of Soderman and Tukaczynski, which I will outline later. And in their case, that the Floer cohomology of a single Lagrangian, you can just take as a model, you can take differential forms on L with coefficients in a Novikov ring, Novikov field. So how are the A infinity operations defined in this case? Well, now you consider the moduli space of holomorphic disks with boundary on L. Now your notion of degree is going to be a relative homology class in H2. And they have K+1 boundary marked points and L interior marked points. So in this case, you have evaluation maps at the boundary, which now map to the Lagrangian, and interior evaluation maps, which map to X. And then the A infinity operations are going to be defined using, as always, like this moduli space holomorphic disks with only only boundary marked points. And again, you can define this using some push-pull formula. So you take a sequence of differential forms on L, you pull them all back to the moduli space, and you push them forward using the evaluation map, one of the boundary marked points. And again, you sum over all holomorphic maps that lie in a given degree. And what is special about our situation, what is really nice, is that actually we can work not just over the Novikov field, but we can work over all bulk deformations. This doesn't make sense to you, don't worry, and just think Novikov field. But instead, we also want to consider all possible bulk deformations by cohomology classes in X. Okay, so now we want to relate the quantum TEP structure to the TEP structure associated to the Fukaya category. And sort of the first step in this was that FO Cubed in 2010 constructed an open-closed map. So this maps the Hochschild homology of the Fukaya category to the quantum cohomology of X. And what does this look like in our setup is basically you can define this using the moduli space now with K+1 boundary marked points and 1 interior marked point. And again, it's some push-pull formula. But now you pull back sort of your whole sequence of differential forms. You pull all of them back to the moduli space under the boundary evaluation maps, and you push them forward using your interior marked point. So this is a map to X. So in the end, you end up with the differential form on X, which lies inside the quantum cohomology. And now Ganatra in 2019 extended the open-closed map to a cyclic open-closed map. So this will map the negative cyclic homology of the Fukaya category to the quantum TEP structure, but he didn't consider the connections yet. And it's very natural to conjecture that indeed the cyclic open closed map is a morphism of TEP structures. And indeed, Gnatra, Perutz, and Sheridan already in 2015 announced work showing that the negative cyclic open closed map is a morphism of TP structures. So, but they only consider the connection in the Novikov direction. So, but they also do prove it for the P structure. But so they don't consider this E structure because they are working in the Calabi-Yau setting, and in the Calabi-Yau setting, this E structure is trivial. So what do? I work in this technical setup of Solomon-Tukaczynski, and then I also construct a negative cyclic open closed map, which will only map the negative cyclic homology of the Fleur cohomology single Lagrangian to the quantum TEP structure. And I show that it respects both the connection sort of in all the base directions, where I'm now working over all possible bulk deformations, and the connection in the E direction. But unfortunately, I'm not able to consider the P structure in this technical setup. Now, what is this technical setup? Is rather strict. So I need to assume that all the moduli spaces are smooth orbitals with corners, and that the boundary evaluation map on the moduli space of disks is a proper submersion to L. Now, fortunately, this does hold in certain situations. And the main example is, for example, when X is projective space and the Lagrangian is the Clifford torus. But more generally, this will work for flag varieties or their products. Now, you might ask, why do you work in such a strict setup? Like, it would be nice if you can prove these things more generally. And the reason is that Solomon-Tukaczynski in this setup defined open Gromov-Witten invariants. And in work in progress, I hope to relate this story about the negative cyclic open closed map to their open Gromov-Witten invariants. And hopefully at the end, I'll have time to talk about this. Any questions? That's either a good sign or a really bad sign. Anyway, I'll continue. So this was the whole story about the TEP structure, so to say, to the Fukaya category being isomorphism to the quantum TEP structure. And now I'll tell you about these splittings, which are going to give us Gromov-Witten invariants. So what is a splitting? If you just have a P structure on E, then a splitting is a linear map from E tilde to E. Remember that E tilde is E modulo U. And it is required to split the natural projection from E to E tilde. And furthermore, we want to like preserve the P structure in a certain way, being that sort of this pairing on E tilde is the same as the pairing after applying the splitting. Now, what is an example of this? If you take the quantum TEP structure, then there is a canonical splitting. So it maps the quantum cohomology of X to the quantum cohomology of X adjoined this formal parameter U, and it's just given by the inclusion of the constants. So it sort of sends alpha to alpha times U to the power 0. And I won't tell you how to go from a TEP structure plus splitting to enumerative invariance, but this splitting is indeed the one that gives rise to Gromov-Witten invariance. So it's just this naive constant splitting. But now what is interesting, suppose that we have two splittings on a TEP structure, then you get this gadget, which is known as an R-matrix. And what is an R-matrix? It's a power series in U of automorphisms of E tilde. And how is it defined? Well, if you can write sort of your first splitting in terms of the second splitting by just applying this automorphism to E tilde. That's all it's doing. It's just like packaging the data of how to relate two splittings. And why are these interesting is because these R matrices act on cohomological field theories. I won't describe how this works, but I will sort of state consequences for Gromov-Witten theory. You can think like if you like cohomological field theories, if you just think about like Gromov-Witten invariants, that will be sufficient for this talk. So one of the things I started thinking about is how you can obtain these R-matrices from the Fukaya category. So suppose that your Fukaya category has some sort of geometric decomposition, which is that the Fukaya category of X splits as a direct sum of Fukaya categories of some other symplectic spaces Yi. Now, what does the cyclic open-closed conjecture give you is that there then exists some decomposition of Tab structures of the quantum cohomology of X, of the quantum Tab structure associated to X, and the direct sum of the quantum Tab structures associated to the spaces Yi. But now the interesting thing is, like on the left-hand side, we have the Gromov-Witten splitting, and on the right-hand side, we also have the Gromov-Witten splittings for each of these Yi's. But in general, if you just have any such geometric decomposition, then this map phi doesn't necessarily need to respect these splittings. So if they are different, then you have two splittings on the quantum Tab structure associated to X, and you obtain an R matrix on the quantum cohomology of X. And it's then very natural to conjecture that in this case, you can actually obtain all genus Gromov-Witten invariants, because that's the data you get from the cohomological field theory. So you get all genus Gromov-Witten invariants of X from the all genus Gromov-Witten invariants of the Yi. So this is some sort of reconstruction theorem. If you want to compute Gromov-Witten invariants of X, you only need to know the Gromov-Witten invariants of all the Yi. And the additional bit of data that you need is that you want to know the genus 0 3-point invariance of X. So that's just quantum cohomology of X as a ring, the very small quantum cohomology.
Kai, you have a question in the chat.
I'm sorry, I can't see the chat. Yes. When do we have such decompositions? Good question. I'm going to give you an example now. Yes. So for example, take the case where this will work for any projective space, but let's just say even projective space, so it actually works on the nodes. And in this case, like projective space is a monotone symplectic manifold, so we can set the Novikov parameter Q equal to 1, so that we just work over the complex numbers rather than the Novikov field. And that simplifies the picture, because now instead of having a full Tab structure, we only have like this connection in the U direction and the pairing, and that just makes notation easier. Now, in this case, the Fukaya category of X, how does it decompose? So you have, as always, for monotone symplectic manifolds, the Fukaya category of X decomposes over these eigenvalues of quantum car product by C1. And in this case, you can show that actually all of these pieces of the Fukaya category are just Fukaya categories of points. So in this case, these spaces Yi are just points, and their Gromov-Witten theory is really, well, it's really simple. So what does this allow us to do is that we get an R matrix for the quantum cohomology of projective space. And this allows you to obtain all higher genus Gromov-Witten invariants. And this was indeed proven that this R matrix that you compute in this way, when they considered, so this is a result by Givental-Teleman, which is that this R matrix indeed recovers all genus Gromov-Witten invariants of X, in this case CP2N, from the genus 0 3-point invariance. So that's just the ring structure. But he doesn't obtain it from this Fukaya category point of view. He obtains it from like, let's say, a more complicated story for cohomological field theories. But it's a really, really nice proof. And in general, Givental-Teleman, like they don't just do this for projective spaces, but they are able to construct such an R matrix and obtain all genus Gromov-Witten invariants just whenever the quantum cohomology of X is semi-simple as a ring. And let me reiterate that in this case, because you have the Fukaya categories of points, sort of they don't have any interest in Gromov-Witten invariants. So all you need is actually just the genus 0 3-point invariance of X, and that allows you to compute all higher genus Gromov-Witten invariants, also genus 0 of projective space. Now, I was hoping to extend this picture to beyond the semi-simple case, because sort of quantum cohomology being semi-simple is in some way like the easiest case to consider. And
Kai, there's a question in the chat, and I have a question for you right after that.
Yes.
I have a
What's the
question too.
Fukaya category of a point? It's just like vector spaces.
Great. And my question was, when you say you obtain an R matrix for the quantum cohomology of CPN,
Yes.
just to clarify, that means you use this decomposition into Fukaya categories of points to construct some splitting. So it's an R matrix with respect to the splitting. You know, you need to compare two splittings, right? So the R matrix comes from comparing the splitting that gives you Gromov-Witten theory of CPN with the splitting that comes from points.
Yes, exactly.
Is that right? Okay.
Yeah. So there, like the thing is that there exists an isomorphism of the quantum tap structure of CPN and the quantum tap structure of like this direct sum of points.
Thanks.
And that isomorphism is non-trivial in the U direction, so it doesn't respect the splittings.
Oh, I had a question as well.
Yeah.
So in the case where you can work over C instead of adding in the bulk deformations, you don't have the T structure. That's what you were saying in the previous slide.
Yeah.
Okay.
Yeah, because sort of like the T structure was first, for example, like different connection in the direction of the Novikov parameter. And now we've set the Novikov parameter equal to 1. So we just like don't consider that direction. But it turns out that is like just this smaller data of just the E structure is actually enough to consider these E structures, to consider the Gromov-Witten invariants and the R-matrices.
Thank you.
So another example in which this happens that's not semi-simple is if you consider the intersection of two quadric hypersurfaces in CP5. So this is also a monotone symplectic manifold. And what is this eigenvalue decomposition? It's you have sort of a minus 8 and plus 8, and then there is a bigger eigenvalue at 0. And what does the bigger mean in this case? Is that it's sort of not the Fukaya category of a point. And what Ivan Smith proves in 2011 is that basically the Fukaya category, sort of this summand 0, is quasi-equivalent to the Fukaya category of a genus 2 curve, which is very much not like a point. And then just from the cyclic open-closed picture, you would expect then that the quantum cohomology, the quantum tap structure of this intersection two quadric hypersurfaces is isomorphic to the quantum cohomology of a point plus the quantum cohomology of a point plus the quantum cohomology of this genus 2 curve. But this is what you would expect from the theorem, but I also checked this by hand. You can actually do some computation. It's unfortunately quite a long computation, so I won't do it here. But you can check that there exists a unique such isomorphism of EP structures. And that's in some way, yeah, for like if you do this statement modulo U, then this was already proven by Donaldson some time ago, but it was very unclear on whether this should upgrade to these tap structures. But if you consider it from a Fukaya category point of view, it's very clear. And in this, what is really nice in this case is that you can actually compute this R matrix. So I've written some computer code that does this for me, compute the R matrix, and you can actually then say something about higher genus Gromov-Witten invariants of this intersection of quadrics. But I don't yet have a proof that indeed these sort of new numbers I obtain indeed are the higher genus Gromov-Witten invariants, because that would require some proof that's very like takes inspiration from Givental-Teleman, and I don't know how to do that. So for now, obtaining these Gromov-Witten invariants is conjectural. Any questions about this?
Quick question. When you say the R matrix is explicitly computable, does that mean you sort of compute both splittings by hand using what one knows about the Gromov-Witten invariants in both cases?
No. So in this case, sort of the splitting on both sides is just sort of going to be sort of the trivial splitting.
Yes, I see. Thanks.
And then
Right.
so the thing that you need to compute is this isomorphism.
Thanks.
And what I prove is that this isomorphism is in sort of inductively constructed. So yeah, for any given power of u, you can compute it using a computer. And I see there's a question in the chat. Can I say why the -8 part is given by a point? No, I don't have any argument for, well, if you follow through Ivan Smith's proof, what you would expect is that these summands are generated by some Lagrangian torus. They're split generated by Lagrangian torus, and then it's actually going to be a Clifford algebra. But from sort of an enumerative invariant point of view, a Clifford algebra is basically the same as the Fukaya category of a point. And this was proven actually recently by a Mormon too. And that's why I was first considering only these even dimensional projective spaces, because in that case, sort of it's actually equivalent to the Fukaya category of a point rather than some Clifford algebra. Does that help? Okay, any more questions before I completely switch track? Okay, so as I said, I hope to also talk about open Gromov-Witten invariants. So that's the next part of the story. So what do Solomon and Dikuczynski do? They define some genus 0 open Gromov-Witten invariants, and this is like the data of this is some sort of counts of holomorphic disks with boundary on your Lagrangian, which have k boundary constraints to lie on points on L. And additionally, they have interior constraints along cohomology classes in X. Sort of, that's the intuitive idea of what you want to count. And what do is they use sort of this framework of open Gromov-Witten invariants to define an extension of the quantum TE structure. Now, how does this go? They consider the integration map over the Lagrangian, which maps differential forms on X to the real numbers. And then they consider just the cone over this map and take the homology. And that's what they call the relative quantum cohomology. And then they equip this with a connection. So first of all, I will only talk about the connection in the Q direction here, because that will be most interesting for the application I have, which is for Calabi-Yau, for the quintic threefold. And the U connection is trivial, so I only consider the connection in the direction of Novikov parameter. So how is this defined? Well, an element in this cone complex is given by a scalar E and a differential form eta on X. And on the differential form part, we just apply the connection that we already knew from before. And what do you do to the scalar? Well, first of all, you have to differentiate in Q del Q, and then you add a U to the -1 term, which is now given by this operator Q -1, 2. Now, how is this defined? This is some sort of basically a count of holomorphic disks where you pull back 2 differential forms on X, and you integrate it now over the moduli space with 2 interior marked points and 0 boundary marked points. So these are ideally what you would define as open Gromov-Witten invariants. The problem is that this operator Q -1 is not going to be well defined on sort of cohomology classes, in the sense that if you take 2 different representatives of a cohomology class, then this number that you obtain is not going to be well defined in general. But the point is that, like, of this cone complex is that you sort of counteract this ill-definedness by taking the whole Cohen complex. So that if you change your eta here, so you have a different cohomology class, you also change it here, so that the total thing is going to be well defined in the relative quantum cohomology. I won't precisely like spell out on why this is well defined, but that's how you should think about it. So this gives you a number, and intuitively that's sort of the count of disks through these two representatives, eta 1 and eta 2. And in the case of the connection in the Novikov parameter, you count disks with one interior constraint on omega and one interior constraint on the differential form eta, which was sort of part of your element of the Cohen complex. And now what is special about this, if you assume that the homology class of your Lagrangian in the homology of X is 0, then this gives you an extension of TE structures. So like this map goes to R, but we have extended coefficients to the Novikov ring. So we get one piece that's just like the TE structure associated to the Novikov field adjoint U, which is just the trivial connection, which is just like Q by del Q. Then you have the relative quantum cohomology, and then it maps to the absolute quantum cohomology. And the idea of obtaining open Gromov-Witten invariants from the Fukaya category is again to mimic this extension of T structures, but now from the Fukaya category. So I'll say next how to do that. Any questions about this? Okay. So this is what I call relative cyclic homology. And this you can define in general if you have just any A infinity functor between two categories C and D, then this will induce a map on negative cyclic chains. So this like cyclic chains on C adjoin the parameter U, and I see a typo here, this minus shouldn't be here, and cyclic chains on D adjoin the formal parameter U.
Well, you
And
have a
then-
question in the chat. Sorry.
Yes. Which map? So if the fundamental class of the Lagrangian is non-zero, then your short exact sequence goes the other way around. So like this is just like you have some. It's basically an exact. It's always an exact triangle, but if the fundamental class of L is 0, then the triangle breaks up in one way, and if it's non-zero, then the map to the Novikov field is going to be surjective. So the triangle splits in another direction. But for open Gromov-Witten invariants, for now, I'm like the main thing to consider is when the fundamental class of the Lagrangian is 0. Yes, so given this A infinity functor F, I construct this sort of negative cyclic homology of this functor, which is just given by the homology of this push forward map on negative cyclic chains. And what I show is that you can construct a connection on this negative cyclic homology of this functor. Unfortunately, I'm not able to show right now that it is flat. And that's what you would need to actually make this a TE structure. And I do apologize for that. But in my application, we don't like the flatness will be for free. So we're going to apply this to the functor, which is given by sort of a Lagrangian, where this star denotes sort of the trivial category. And we map that to the Fukaya category by including the Lagrangian. So this star has just home space between this one object. It's just going to be given by the ground field, which in the case of the Fukaya category is the Novikov field. And it's just inclusion of that Lagrangian. And this thing, just to be very clear about what it is, it's the negative cyclic homology of the Fukaya category relative to this Lagrangian. And in this case, we're very lucky, is that actually this negative cyclic homology gets like this connection that I construct on it, it's just flat. And in this case, it's like really easy to show. And moreover, if you assume that the Chern character of your Lagrangian, which for me means the class of the unit on this Lagrangian, is 0 inside the negative cyclic homology of the Fukaya category. This is like under the open closed map. This corresponds to your Lagrangian having 0 fundamental class in X. Then you have some short exact sequence again of TE structures, but this one goes the other way around. So you have the absolute negative cyclic homology to Fukaya category that maps to the relative cyclic homology, and that maps to the Novikov field to join U. So we need to dualize somewhere to make these things agree. And I have chosen to dualize on the quantum TE structure. So we now consider instead what I call the relative quantum homology, which is just a dual TE structure to the relative quantum cohomology. And it's very natural to conjecture that there then exists some extension of the negative cyclic open closed map, some relative cyclic open closed map, which relates the relative negative cyclic homology of the Fukaya category with this Lagrangian L to the relative quantum homology. And in general, you expect that to fit in some exact sequence like this. Note that I've also here have to dualize the cyclic open closed map from before. So what I was really saying is that if you consider negative cyclic open closed map, you really should map to quantum homology rather than quantum cohomology. And what do I show is that under these assumptions of before, like the Solomon-Tukachinsky assumptions, that this conjecture will hold. And instead of the Fukaya category of X, you need to take the Fleur code chain complex of a single Lagrangian. And the idea is that this exact sequence will give us some information about open Gromov-Witten invariants. And indeed, if we assume that that this conjecture has been proven for the Fermat-Quintic threefold, which unfortunately the technical setup I use doesn't apply in, but then you can show that just the data of this short exact sequence is enough to recover all open Gromov-Witten invariants of the real locus inside the Fermat-Quintic threefold, which were recently considered, like these open Gromov-Witten invariants were recently considered by Walcher and Hahnenbacher and Solomon Pandey-Walker, where they actually compute these open Gromov-Witten invariants and have like a conjecture for them, and have some sort of what they call like an extension of sort of the classical picture of these closed Gromov-Witten invariants and periods. They upgrade this to a picture involving open Gromov-Witten invariants, what they call extended periods. And the hope would be that this is also implied by a homological mirror symmetry. So this result shows that, at least on the symplectic side, we very much do expect this. Cool. And I won't go into a proof of this statement, so let me finish there.
Did you say you're finishing the talk? I'm sorry.
Yes. Let's thank Kai for his talk. If I go into the proof, it will take too long.
No problem. Let's thank Kai for his talk. Thank you. Questions for our speaker?
Yes. So for the first theorem in this page, does this mean the L would generate the Fukaya category or not?
No. This is just the result. So no, it doesn't, because you also have to replace the Fukaya category here with just this Fleur cohomology of the Lagrangian. So that means that if L doesn't generate the Fukaya category, which for a single Lagrangian is going to be very hard in the Calabi-Yau case, then this map is definitely not going to be an isomorphism. Oh, so it simply means that this is just a map of exact sequences, which makes the diagram commutes, but not saying that it's an isomorphism of sequences. Yes, exactly. Okay. Yeah. Okay. But indeed, if this map here is an isomorphism, then of course this one is also going to be an isomorphism. And that is very much expected if you consider the whole Fukaya category of X rather than just the Floer cohomology of a single Lagrangian. But as Abu Zaid told me that he was very much not worried about this, because if you would consider some sort of immersed Lagrangians, then you can always just take a direct sum of all the Lagrangians that you want and consider that as one Lagrangian. But our technical setup definitely doesn't apply in that setting.
Okay. Okay.
I know you didn't want to go into the whole technical details of the proof, but are there any quick words you can say about the proof or any like aspects of it?
Yeah, thank you. That's a very nice question. So what is the idea? That you take this TEP structure associated to the Fermat-Quintic threefold, and you let L be the Lagrangian. And in that case, these TEP structures, because we're working in a Calabi-Yau setting, are all Z graded. So instead, you can just talk about the variation of both structures. And this is just setting U is equal to 1 in the TEP structure. So indeed, you lose all this information of the E structure. And in that case, what is just like the connection on just like quantum cohomology is just given by Q bubble Q and quantum cup product with omega. And we have dualized the exact sequence to get this. And what Han and Walker show is that there exists a unique element in this relative quantum homology. So this is just some VHS, which is flat for this extended connection Q by del Q, and lifts the element 1 inside coming from the Novikov field. And moreover, is uniquely defined up to addition of a constant multiple of the point class coming from here. And what is special about this? Usually, if you consider flat sections for this quantum connection, is that these are going to have monodromy. But this section H doesn't have monodromy, which is why we can specify it. And in like, for say the quintic threefold, there is one flat section in the quantum cohomology of X, which doesn't have monodromy, and that is the point class, which is why this point class shows up. And then another piece of data that you can construct, just like from the extension of TP structures, is a functional, which is pairing with the holomorphic volume form, which in the case of quantum cohomology is just the unit, or like the fundamental class inside the quantum homology. And this is just a linear map from the relative quantum homology to the ground field, which is the Novikov ring. And so what does this give you? It gives you that this pairing of the holomorphic volume form with this element H is going to be uniquely defined inside the Novikov. Well, now you have to work out the Novikov ring, but you can do this for the VHS. And sort of, or if you consider it as a power series, sort of the only term that you don't like get from this is just a constant term. But all higher order terms in Q are going to be uniquely defined. And you can do just a simple calculation to show that in this case, this is actually the open Gromov-Witten generating function. So this pairing of the holomorphic volume form with this extra flat section H gives you all information about open Gromov-Witten invariants. And the goal is to obtain this from the VHS associated to the Fukaya category. And this is really nice because this was already done by Ganatra, Roots, and Sheridan. So what they do is they show that this holomorphic volume form in the VHS associated to the Fukaya category is just determined intrinsically by the data of the VHS. So that's saying that the Fukaya category knows about this holomorphic volume form. And indeed, because the negative cyclic homology, the relative negative cyclic homology of this Lagrangian is isomorphic to the relative quantum cohomology, such a flat section H is also going to exist. So just these facts together will give us that this pairing omega comma H is just already data that is contained inside the Fukaya category, which is the open Gromov-Witten generating function. So yeah, that finishes that proof.
Other questions for Kai?
I forgot to say, by the way, this second part about open Gromov-Witten invariants, everything I talked about before that is already up on the archive. The second bit is not yet up in the archive and will hopefully be next month. Everything is written. I just need to like polish it. So apologies for that.
Great. Well, let's thank Kai again.